Great, thank you. I'm going to take back control here for a few minutes, and we will put up a timer until we'll start the next speaker at the top of the hour.
Very good. Thank you.
Thank you. All right, welcome back. I am going to change our presenter over to Andrew Macpherson, and while he gets set up, I will introduce him. Andrew Macpherson comes to us from Prism Training and Consultancy. He has over 20 years of software development experience and enjoys the most challenging data management, statistical visualization, and analysis problems. He is managing director of Prism TC. He has executive responsibility for the business. He also maintains the company's statistical software tools, curates their library of training materials, and is a course instructor for a number of their online and on-site workshops. Andrew loves using, adapting, and making software, and his programming, data management, analysis, and visualization skills are well suited to a wide range of useful applications. Andrew has produced countless macros, scripts, automations, and programs for more than 20 years. These greatly assist Prism's clients and allow the other Prism team members' ideas to become valuable software tools. Andrew also plays a key role in moving an ever-expanding range of statistical tools to the website, making them freely available to everyone. So, Andrew, we would like to welcome you, and the floor is yours.
Thank you very much, Sherry. Hello, everybody, and thanks for that excellent introduction, Sherry. Before I go any further, can I just do the inevitable, can you see the right screen, please, Sherry? Are you able to just see the main slide? Excellent. That's a promising start then. Thank you very much.
Yep, can see it and hear it.
Lovely, thank you. So there's the title slide for my talk today, and there's a mugshot of me, which is the main reason why I'm not going to be sharing my camera. I think that's probably all you want to see of me today. So without any further ado, I will move on to give you a little bit of background about our company. Now, we're Prism Training and Consultancy. We're based in the UK. I appreciate the majority of the audience today is probably based in the States. So please take a moment to feel sorry for us over here, because we're going through a pretty bad time at the moment. But let's leave that to one side for the moment. We're an independent company. We offer a range of statistical services. We do training, we do consultancy, and we do software services as well. We've been around for 20 years or so. We've got a small but excellent team of statisticians, trainers, programmers, and scientists, and we support quite a large client base across many industries around the world. We've been a Stat-Ease reseller for almost a decade now, so I'm hoping I don't say anything too appalling that will cause us to miss our 10-year anniversary in 2023. The purpose of my talk today is really to talk about Stat-Ease's latest software product, Stat-Ease 360, and hopefully spark some ideas about how we can all take advantage of it, because it puts some really useful flexibility and firepower at our fingertips and allows us to go beyond the standard everyday DOE tools that we've been using for many years in Design Expert. Now, as an illustration, something to talk about to try and show you what we could do with Stat-Ease 360, I'm going to revisit some topics that my colleague, Dr. Paul Nelson, our technical director, actually discussed at one of the previous Stat-Ease DOE Summits back in Paris a few years back. If you want to take a look at the slides when they're posted online, I'd certainly encourage you to take a look through Paul's presentation, which goes into a lot more detail about definitive screening designs than I'll aim to do today. Because really what I want to try and do today is show you how we can use Python to extend the functionality of the everyday tools that we use and really strive for the impossible. A lot of us have heard of definitive screening designs, and I think most of us are aware that they're extremely interesting, but they present some very specific challenges, and it can often be quite difficult to know what the best model is for a definitive screening design. So that's the impossible task we've set ourselves as a way of trying to illustrate to you how Stat-Ease 360 can be a very useful tool to try and solve specific, potentially niche problems. Now, I don't want to spend the whole day going on about DSDs. We've probably all heard quite a lot of hype around DSDs over the years. So the last thing I want to do is endlessly talk about DSDs. The subjects I will touch upon are listed here, and we'll move straight into a quick discussion around, the main differences between Design Expert, which I imagine most of us are quite familiar with, and the new product, Stat-Ease 360. Now, Design Expert, in my humble opinion at least, is one of the most user-friendly DOE packages out there. It's the main reason we were so keen to be the reseller for this product. It's a great piece of kit, and it gives us everything we will need in the vast majority of cases. But there's always the exception to the rule, isn't there? And occasionally we may wish or need to do something that's just outside the scope of the standard toolkit. As one simple example, in some of the training courses that we deliver, we suggest to people that they might want to consider something called a scoping design as a very simple exploratory first step before they embark upon a proper set of DOE studies. And the diagram here on the right is just intended to show you that these are very, very basic tools. They're purely sort of visual assessment of what kind of shape your process is in. Now, they're very simple to look at, but because they are so simple, it's actually a little bit of a challenge to set these up in Design Expert, because Design Expert is solely geared towards building good designs. And the honest truth of it is a scoping design is not a very good design. So actually building one of these simple tools is not as straightforward as we might like it to be. So what we did for this particular one-off niche problem is we built a tool that we've hosted on our website. And this is fine for us. We can justify doing this because we talk about these scoping designs a lot in our training courses, and we deliver a lot of DOE training. So for us, it was worth the hassle and the time and the cost of developing a website that allows us to host interactive tools. And we then built this scoping design builder tool. We reverse engineered the DXPX file format in order to build this interactive functionality on our website, where somebody can punch in their factors, their responses, set their design parameters, and have it build a DXPX file, which you can open up directly in Design Expert. So this is one example of a niche problem, which we had to invest quite a lot of time and effort in solving. Why I'm so excited about Stat-Ease 360 is that we don't have to go outside the Stat-Ease environment anymore. If we've got access to Stat-Ease 360, then we've got everything that makes Design Expert so good, and a whole lot more. We've got all this power user functionality, much more advanced and complex, specialized designs that may have particular uses that I've not had a chance to explore yet. But the bit that really excites me is the Python integration, because this suddenly opens up a whole world of possibilities. And it's up to us to really decide how we're going to take advantage of that. Now, you've probably all heard of Python. Ivan spoke about it a little bit earlier on today. So I'm not going to go into any great detail about Python, other than say it's obviously a very popular programming language. It regularly ranks pretty highly amongst the most popular, most widely used programming languages. I had a quick look earlier and found it's currently ranked number 4, just behind JavaScript and HTML and SQL in a recent survey. So it's always up there near the top of the most popular and widely used programming languages. It's open source, and it's also very easy to pick up. As programming languages go, they really emphasize and prioritize the readability and simplicity of the code that they want you to write using this Python language. And it's a very powerful programming language. And if it can't do what you need it to do, it's extremely extensible. And you can easily download packages and modules to really ramp up the functionality that you can call upon. So it's an extremely easy software programming language to pick up and get the hang of. And you probably appreciate. It's named after Monty Python. I put a little British flag there again because it's a bad time to be British. So we're clinging on to anything that might give us some cheer at the moment. And that's our sole stake to glory at the moment. If you want more information on Python, there's an absolute ton of freely available resource out there. The python.org website is the obvious place to go. And just again, because the best jokes, the ones you have to explain. The title of the talk today, Python and the Holy Grail. We kind of figured it all sort of tied together rather nicely. hence the somewhat convoluted title of this talk. And before I go into any more detail, I just want to set down a couple of disclaimers. Arvid said something similar earlier, which is he doesn't claim to be a Python expert, and I certainly don't either. My knowledge and experience of Python really starts and ends with the tool I'm going to show you today. So I'm using this talk as an excuse to have a play with Python. I'm certainly not going to be telling you how you should or shouldn't be writing code in Python, because I'm by no means an expert. But what I want to try and show you is it's easy to do. I'm also not a proper statistician. There's a joke, what do you call a guy who hangs around musicians? The drummer. And I hang around a lot of statisticians. I'm not quite sure what that makes me, but I'm the equivalent of a drummer in the statistics world. And over the years, I've probably absorbed, unwillingly, I'd probably say, a fair amount of statistical knowledge, but I certainly wouldn't claim to be any kind of expert in the subject. So why am I talking to you today about two things I profess to know little about? Well, it's because this kind of forms part of the area that I do like working in. I like solving problems, and the work that I do with Prism is in this really nice sweet spot. Our customers are scientists, and my colleagues are statisticians, and we use software all the time. And the bit that gets me interested and excited is seeing the combination, the overlap between these three areas, and trying to figure out how we can make the software and the statistical methods solve the scientific problems. So this is what I enjoy doing, and this is why I'm likely to embarrass myself today with my lack of knowledge about statistics and Python. The real reason I want to do this is to show you that it is possible. And I appreciate this statement here sounds a little bit condescending, but it's not my intention at all. I mean this with absolute sincerity, that if I can pull together a Python tool just through hacking away at it and modifying bits of code I can find online, it will hopefully demonstrate to you that it's actually very easy to do. And that's really the goal of this talk. Now, we've developed an app using Python to try and solve this DSD problem, but it's solely as an illustration. So I'm going to talk a little bit about DSDs in a moment and a bit about Python, but it's just to provide some sort of context and an example to show you how we might identify and then go about solving a real world problem. Really, what I want to do is try and provoke a few thoughts in your heads about what problems you might encounter regularly that you could perhaps think about addressing through an automated method, through some kind of guidance through the form of Python that your users could take advantage of to perform better analyses. So it's really all about just trying to show you the simplicity, the potential of Stat-Ease 360's Python integration. As I say, we're going to use definitive screening designs as the case study that I'm going to be looking at today, and many of you will be very familiar with DSDs. And for those of you who are not, I'll just spend a couple of minutes giving you some of the basics about these designs. They're relatively new in the world of DOE. As many of us know, DOE has been around for about a century or so, and these DSDs have only been around for a decade. So they are fairly new developments in the world of DOE. If you'd like to know more about definitive screening designs, we've got an article on our website, which you're very welcome to take a look at. Again, that's written by my colleague, Dr. Paul Nelson. So I'd certainly encourage you to read up a bit more about them if what I'm about to tell you piques your interest at all. Now, really, these definitive screening designs should be considered screening designs. That's kind of there in the name. The way that they're constructed is with these three levels of each factor. The structure of the design forms this interesting and somewhat unique fold-over pattern, which gives the design certain interesting and potentially beneficial quirks. But ultimately, as I say, as I put in bold here, I think it's sensible to view these DSDs primarily as screening designs. And they allow us to screen our factors fairly efficiently. That is, they allow us to estimate the main effect of our factors with just 2 times k plus 1 runs. So if we have k factors, we know straight away that we can estimate the effects of those factors fairly quickly and fairly easily. Where the definitive screening designs become particularly interesting, and this is the bit that really grabs a lot of people's attention, is the possibility that we might be able to fit a full response surface model to our factors. Now, the word sometimes is doing a lot of heavy lifting in this sentence, because on occasions, if the stars align, we can fit quite a complex model to our factors in a very, very efficient design. If we're considering 6 factors, we're doing 13 runs, the ability to fit a full response surface model that looks at the effects of the factors, their linear effect on responses, the interaction between all of our factors, and the non-linear behavior of those factors, that's a lot of complexity. The trouble is that we can't always fit that full response surface model. And the details or the explanation really comes down to this thing called degrees of freedom. And I apologize for any statisticians who are listening who may take issue with what I'm about to say, but we suggest thinking about degrees of freedom fairly simply as just information, pieces of information. The more runs you perform, the more information you have at your disposal, and the more things that you can estimate. Definitive screening designs are what we call supersaturated designs. That is, the model that we might want to fit demands more degrees of freedom than we have available from our chosen design. And if we take the example of a 6-factor study, if we wanted to fit the full response surface model, it would demand 28 model terms. However, with 6 factors, we'd only have performed 13 runs. And clearly, we cannot estimate 28 effects if we've just performed 13 experiments. So this is the big limitation, that we cannot fit the full response surface model to all of our factors. However, if we get lucky, and that's a big if, but if we get lucky and 3 or fewer factors turn out to be active, then the way that these designs are constructed is really quite interesting. Because what happens is this design kind of collapses or projects down to any 3 factors and allows us to fit a full response surface model to those 1, 2, or 3 factors. So that's pretty cool. If things work out nicely, we've got a lot of very complex information out of a very efficient design. But we don't know what's going to happen. We don't know whether we'll be able to fit this full response surface model or not. And this is probably at the heart of a lot of people's concerns around these definitive screening designs. So how should we consider them? You know, what should we expect of them? Now, in my opinion, it's fairly clear to say that if we're expecting a full response surface model for all of our factors from 2 times k plus 1 runs, then you're setting yourself up for disappointment. That's just not going to happen. So what we suggest when we're talking to our customers about, you know, the relative merits of a definitive screening design, and that they've heard the hype and they want to know what's possible, what we try and do is kind of just set their expectations a little bit more realistically and say, well, look, it's a definitive screening design, so let's just expect that we're going to be able to estimate our main effects and view them as a screening design. And maybe, just maybe, we'll get lucky. And maybe, just maybe, if we believe that sparsity of factors is likely, then this definitive screening design could be a really smart choice. Now, sparsity of factors is quite a divisive subject, I think it's fair to say. And I'm going to steer completely clear of this debate because I'm not going to get into the question about whether the scientists we work with are so incompetent that they're going to be choosing a design where half of their factors turn out to be completely irrelevant. So if we think that sparsity of factors might be likely, then definitive screening designs are superb. If we think most factors are pretty likely to be doing something, then perhaps DSDs are not the best choice for us. So I'm not going to get into the debate about whether we should or shouldn't choose a DSD. What I want to focus on is the situation where we're dealing with somebody who has chosen to run a DSD. And what we want to do is ensure that they make the best use of that design. And what we're going to do to try and illustrate this is take a case study, and it's a purification example, looking at recombinant Fab in E. coli. We've got a diagram here, which is a generic HPLC system. And of course, we can set up our definitive screening design using Design Expert or Stat-Ease 360. You'll see here, hopefully you can see my mouse cursor. We've picked here the definitive screen option underneath the response surface group of families. We fed in our 6 factors that we believe are likely to be important and define the ranges. We've gone through the process and built that design. And you can see here that this is the resulting design. I've sorted it by standard order. And you can see we're awaiting our results. So that's how we might go about setting up a definitive screening design using Design Expert or Stat-Ease 360. The challenging bit, in my opinion, comes when we come to try and analyze that data. Because Design Expert and Stat-Ease 360, they give us the tools that we use every day. And for most standard designs, they're more than adequate. We've got lots of different model selection methods. We can use p-values, we can use AICC, we can use BIC, we can use adjusted R-squared. We can work forwards, backwards, stepwise. And again, I know these questions were cropping up earlier with Arvid's talk. So we've got lots of tools here that will help us in almost every situation. But unfortunately, of course, DSDs is one of those exceptions. And the unique structure of definitive screening designs causes unique challenges, and it often makes it quite difficult for our general purpose model selection tools to make much sense of this data. We've got a screenshot here of the fit summary output that you can get from Design Expert and Stat-Ease 360. You can see here it's not even attempting to assess the 2-factor interaction group of effects because there's too much aliasing present. And that's just the nature of these definitive screening designs. We've got partially aliased second order terms. We've got a supersaturated design. So it's quite a difficult set of data to make much sense of. So what we're proposing is that if we're going to analyze a definitive screening design, then we might need to move away from the standard tools and try and come up with a way of analyzing definitive screening designs that's specifically geared towards definitive screening designs quirks. And in fact, the people who introduced definitive screening designs, Brad Jones and Chris Nackstein, actually identified and have now recommended a DSD specific method that really does maximize the benefits of these DSDs. And it really exploits the structure, because the structure of these definitive screening designs is such that our main effects are completely orthogonal to the second order terms. What that means is we can estimate and assess these 2 groups of types of effects completely independently from one another. And if we know that our structure offers certain properties, we should really be trying to choose the right tool for the job and making as much use of that knowledge as we possibly can. And that's what this recommended DSD specific method does. So I'm going to go into a little bit of detail now about what their recommendation is, how this analysis works, and in a few moments time, what I'm going to do is show you how we've started to develop a software tool that implements this. Now, the recommended design-oriented approach is, rather than analyzing each response as we record it, is to take each response, which we usually label Y, and split that column of data into 2 pseudo responses. And we label these pseudo responses YME, Y for main effects, and Y second, Y for the second order effects. And then we go through a 2-step analysis approach. The first step, first and foremost, let's figure out which factors are active. And then, if we determine that 3 or fewer factors are active, then we can go further. And we can assume hierarchy, which will limit the number of things we need to consider. And then we can try and figure out which is the best hierarchical set of second order terms, that is interactions and quadratic effects, that result in the best model. And I quite like this, not being a statistician, just being somebody who's aware of DOE and aware of some statistical theory. To me, this is quite a sensible, practical, pragmatic approach. It's kind of reacting to what the data is telling us, rather than just blindly going in and throwing some generic analysis method at it. What we're doing is we're looking carefully at data. First of all, let's assess the factors. And if we get one set of outcome from that, we can go further. And if we don't, we have to stop. But we're doing everything we possibly can to squeeze every last drop of understanding out of our data, which I think is incredibly good practice. So let's just provide a little bit more detail around these 2 pseudo responses. Step 1, it's all about this pseudo response, which we term YME. Y to look at the main effects. And the goal of this first step is to identify which of our factors are the most important ones. Now, what we do to build this YME response is we build, first of all, a main effects only model for our original response. And we then predict the expected value for each run in our table. And those predicted values form our YME pseudo response. And then what we can do is use a fairly standard forward selection method using a p-value cutoff to identify which of our factors are explaining enough to be identified or flagged as being active. There is a slight caveat, and again, it comes back to the unique structure of these DSDs, and that is we can't apply or assume standard things because of the way these designs are structured. Not all of our observations are truly independent. And that has an impact on our degrees of freedom, how much information we really have to make sense of. So what we have to do with this approach, and it's another little wrinkle in our otherwise smooth analysis workflow, is adjust the degrees of freedom when we're calculating the p-values. So again, we can't use standard tools. We have to make these adaptations and adjustments to ensure that what we're doing is valid and appropriate. So again, it's taking us away from a standard set of tools, forcing us into this position where we're having to think about customizing or building a bespoke analysis method. So once we've gone through to step one, we've created this YME response. We've identified which of our factors are significant through the forward p-value selection. We're at a kind of a stop-go decision point. If we have more than 3 active factors, then we've gone as far as it's sensible to go. Our supersaturated design doesn't contain enough information to allow us to start to consider our second order effects. And we may think, oh, well, that's a shame, we failed. Well, I wouldn't view it quite like that. I would say, well, okay, we failed if our goal was to estimate the second order terms. But if we think about this as a screening study, then what this will have shown us quite efficiently is it's confirmed our knowledge of the process. It's confirmed that our selection of factors was a pretty smart selection of factors. That is, most of them are important. They matter. And that gives us pretty clear steer on what we may need to do next. We might need to augment our design to allow us to estimate more effects, throw some more degrees of freedom at the problem, and we can hopefully start to make more sense of the complex second order terms. So that's almost the bad outcome, that most of our factors turn out to be active. In terms of our DSD analysis, the nice, the interesting, the exciting outcome would be if 3 or fewer factors were active. Because if that's the case, then we get let through the gate, if you like, through the gate into step 2. And we can now start to consider not just the linear main effects, we can also start to think about the second order terms. And in order to assess these, we construct a second pseudo response, which we label Y second. And this is just the difference between our original response and our YME response. A simple subtraction. Now, all of these numbers are easy enough to calculate. It will just take a bit of time to do it manually. So again, it's leading us towards an automated, convenient method. Now, going through the process of reducing the number of active factors down, the benefit of doing this is to reduce the number of potential second order effects that we need to think about. And we're going to assume that our model will be hierarchical. So for example, if we identify that only factors A, B, and C are active, then the full set of second order terms we need to worry about are the A, B, AC, BC two-factor interactions plus the A squared, B squared, and C squared terms. So it's a much more manageable subset of second order terms. And once we've identified what that hierarchical set of second order terms is, we can then try and figure out which potential set or subset of those second order terms gives us the best model fit. And the method that I'm going to be showing you in our tool uses the adjusted R squared metric. We try every possible selection of the hierarchical second order terms, and we pick out the set that gives us the highest possible adjusted R squared value. Now you'll note my little disclaimer or note here. This is following the method that was originally proposed by Jones and Naxtime in 2017. Subsequently, they've reviewed it and decided there's another better method in their view. That's absolutely fine. You know, I don't care, to be blunt. The purpose of this tool is to show you, you know, the possibilities rather than claiming this is the perfect DSD analysis tool. So for the purposes of a demo tool, I'm going to go with the slightly more antiquated 2017 recommendation. Now, usually in the evenings, my wife sticks on the telly and she usually watches a program about baking cakes or something equally exciting. What I usually at that point is doodle, listen to some music or something. But on one particular evening, I happened to be thinking about this talk and started to map out how I was going to tackle it. And again, this is where we're starting to get into thinking about software development. Now, I'm not a proper software developer. I'm more of a hacker. I'm a pretty crude programmer. If I want to solve a problem, what I'll do is I'll go and Google and find some code that's similar to what I want to achieve. And then I'll hack away at it. I'll change bits and I'll add bits and I'll copy and paste something else I find online until it does what I need it to do. So I'm not claiming my method is in any way elegant or efficient, but it's effective. It gets the job done. And this is kind of how I've tackled this. And I've thought through, you know, just very basically what it is I need my code to do. And you can just about make out, if you can read my appalling handwriting, that I want my Python code to first of all calculate these YME values. Now, again, I could do this manually, but if I can automate this, it's going to save me so much time. I then want my Python code to try fitting the main effect to this YME pseudo response. I'm going to use a forward p-value selection method. I need to adjust or correct my degrees of freedom when I'm calculating those p-values. And this will tell me how many factors appear to be important, how many factors appear to be active. And if it's 3 or fewer, that's awesome, because then I can move on to step 2. I can create my Y-second pseudo response, and I can then start to assess my 2-factor interactions. I can assess my quadratic terms, and I can try fitting every possible hierarchical model and identify the best one, that is the one that has the highest adjusted R-squared metric. And then at the end of all of this, having separated out my identification of the best factors and the best second order terms, the final step is to pull it all back together again and fit the combined model involving the factors and the second order terms back to my original response in Stat-Ease 360. And just to put the cherry on top of all this, wouldn't it be nice if I could do it in a user-friendly way? So rather than forcing my users, my hypothetical users, to go through some command line interface, some terminal type input, wouldn't it make it easier for them if I could come up with a nice user-friendly dialogue they can just point and click at and be forced into analyzing their data properly? Well, you can probably guess where this is going. Otherwise, it's going to be a disappointing anticlimactic end to the talk. But we got there, or we've got somewhere. I won't say it's perfect, but it's definitely on the right path. Now, to get to where I've ended up, and I'll show you that in a moment, you know, I built this up step by step, naturally, organically, sensibly, logically. Let's just take this one step at a time. Now, the very first thing I had to do was install Stat-Ease 360 and follow the very user-friendly, idiot-proof instructions to download, install Python, and get Python talking to Stat-Ease 360. That was the first thing I did. And then again, it's really nice that all the instructions that I need were there in the help menu within Stat-Ease 360. It made it very straightforward for me. Once I'd established that I could get Python and Stat-Ease 360 talking to one another, then that's suddenly where I can really start to amp up the functionality. And I took advantages of a number of Python modules to save me having to reinvent the wheel. And this is one of the beauties of Python, of course, is that I don't have to develop my own least squares fit algorithm. I just take advantage of one that somebody else has made for me. So it saves a huge amount of time. And my job really is just kind of daisy chaining one existing function to the next and just joining the dots together. I then moved on to my version 2 script, which is starting to think about the step 2 path analysis, generating all possible subsets of my second order terms, and then picking out the best model by the adjusted R-squared metric. And then finally, again, the sort of the cherry on top, can I make this a bit more user-friendly? Can I create a dialogue to help the user select their choices, show them results, and go back to Stat-Ease 360 and fit the best model to get people back into the environment that they're familiar with. And the good news is that I was able to do all of this. Now, again, I'm not claiming for one moment that what I've developed is a perfect tool, because it categorically is not. But what I want it to do is show you that it's very easy to piece together tools that can make our lives a lot easier. And what we have here is my definitive screening design, looking at it in Stat-Ease 360. And as David showed us earlier, it's actually very easy for us to access Python through Stat-Ease 360 via this script editor button. And once I've fired up this window, I've got the full firepower of Python at my disposal. And on the left, I can write code. It's not very good code, but it's code. On the right-hand side, I've got my Python window, which will show me the results of running the code on the left. What I'll do is I'll just quickly show you a couple of iterations I went through in developing my code, just to give you a flavor of how quickly you can build these things up. I'm not going to worry about saving that. And this is my first ever Python code. Genuinely, the first bit of Python code I ever wrote was this. And you can see it's not that impressive. I've probably spent longer writing the copyright statement at the top than I did copying and pasting the sample code that's available in the Stat-Ease 360 tutorial. And all I'm doing here, very, very simply, is just trying to establish that connection between this Python window and Stat-Ease 360, just to check that I can talk between these two software interfaces. And these first few lines here are very much copied and pasted straight from the tutorial. And then what I want to do, again, just to see how Python outputs the results, I'm just printing the results. So this is not in any way at all exciting. But look, when I click this button, stuff happens. So I get excited. And on the right, I can see, wow, it's worked. The factors of my current design are flow rate, gradient load, and so on. My responses are resolution, flow through the fabric area and time. So I've now satisfied myself that I can use Python to pull things from Stat-Ease 360. And later what I'll do is I'll push things back into Stat-Ease 360 when I've got results to a point where I want to put them back into my favorite piece of software. Now, going from what I called version 0 here, just that initial test, to version 1, it's quite a big step up. Again, this took quite a while of me just tinkering and playing and learning a little bit of Python along the way. But you can see here that what I'm doing is I'm taking advantage of the standard or existing functionality that Python lets us tap into. So I've imported a few modules to save me having to redefine other people's functionality. So for example, rather than having to figure out the complexities of generating a least squares fit and generating all the associated statistics and metrics, well, I don't need to do that because stats models have done it for me. So I'll just import that module and save myself the time. And what this version 1 script does is it works through step 1 of the recommended DSD analysis. And in this case, I've specified a couple of lines of code where I tell it which response I want to look at. So I'm going to look at my first response here, resolution, and I've defined a p-value cutoff, which I want to use to decide which of my factors are active. Now below this, you'll see I've got lots more code. Incredibly poor Python code for anyone who can write good code. It's not what you should be doing, but it does the job, because when I click run, I get my little report over here on the right. And it's starting my forward selection from my YME pseudo response for resolution. It's adding the largest main effect first, and then it's trying to add the next biggest effect. And if this p-value is less than my chosen threshold of 0.1, it lets flow rate through as well. It lets pH through as well. It tries load, the next factor, but it says, no, you're not important enough. Your p-value does not satisfy my p-value criterion of 0.1. So therefore, load does not get identified as being an active factor. So having performed this forward selection method, I've identified that my best model for my YME pseudo response involves factors A, B, and D. And this is as far as my version 1 code goes. It just says, okay, we've got 3 active factors. So what we should do next is move on to step 2. And that's what my version 2 code will do. And all I'm doing with each evolution of my code here is adding a bit more functionality, just building it up one step at a time in what I hope to be a fairly logical way. What I've added here is this itertools module, which allows me to very quickly and easily produce every possible subset of a group of effects. So I use this to look at every possible subset of second order terms. So that's step 2 analysis. And again, I'm looking at resolution with a p-value cutoff of 1. And I'm going to run this script, and we'll see that now it performs this first step again. And this time it's going to go further still. Just takes a second, and here we go. So again, this part of the output is exactly the same as before. But now, because it's recognized it's got 3 or fewer active factors, it also now moves on to take a look at the second order terms. And it tells me what the best hierarchical second order model is, as well as reporting the adjusted R-squared value. And then, as I mentioned from my school's notes and my notepad slide a moment ago, it combines the important factors with the best hierarchical second order model to form the overall recommended model, which for this particular response is the intercept plus factors A, B, and D, plus all of their associated 2-factor interactions, plus B squared plus D squared. So it's almost the full response surface model. The only missing term there will be the A squared term, because that wasn't deemed to be useful enough according to this adjusted R-squared metric. And this gives us everything we need to implement automatically a version of the recommended DSD analysis method. Now, as I say, it's not perfect, the method, the way I've implemented it, but it's a pretty good approximation, I think. And I hope it's close enough to show you that it's actually quite easy to build up this type of functionality just by going step by step, seeing which modules offer the type of functionality you want and how you can adapt them and tweak them as required. Now, the final step that I went to was to add on a graphical user interface to make this a bit more user-friendly. Now, I have no intention of giving this to anyone because I know this code has not been properly tested. But if I was working with a group of scientists, say, who regularly ran definitive screening designs, I would want to make this tool as easy to use as possible for them. So I think it's a sensible investment of time to build a graphical user interface that's going to force them to use the tool properly. And when I run this, my dialog will inevitably, of course, pop up on the wrong window on my computer, so I'll just drag this across. But what we'll see here is a dialog. Not a very exciting one, certainly not a pretty one. I apologize for the horrible color scheme that Python seems to default to. But what we can see now is we've got some options that we can point and click at, and I can choose which response I want to analyze. I don't have to type this into some arbitrary line of code buried somewhere deep within my script. I can choose to look at the resolution response. I can choose what the p-value threshold I want to use for that step 1 main effects model selection. If I click a p-value of 0.1, then it performs that analysis again. But this time, rather than having to go into some console window, some command line interface type thing, it shows me all the results right here in this dialog, and it tells me at which point it's stopped adding factors. It highlights that in red to say load was not added because the p-value wasn't significant enough. And again, as before, it shows us what's been fitted. So it shows us what's been recommended as the model to fit. And with this version of my script, it actually goes and fits this in Stat-Ease 360. So after pulling out the response information, the factor information, what I'm now doing is I'm putting the results back into Stat-Ease 360 to allow the user to get back into their familiar environment. They can exit this now, go back in here and take a look at the model as it's been fitted in this resolution response at the end of a table, and the user will go, oh, hang on a minute, that AD term doesn't make any sense to include, so I'll go and remove that AD term manually. And of course, it's exactly what they should be doing. But what I think is good about this is that that's the only sort of decision they're now having to worry about. They're not having to go away and calculate all the horrible calculations and sums and predictions and everything else that's needed to build these YME and Y second pseudo responses. They're not having to adjust degrees of freedom to calculate p-values correctly. All they're doing is applying their knowledge to look at this start point of the recommended model, and then they can decide, well, do I think this interaction should be there or not? Could I fine tune it? Could I remove this? Does this make sense? You know, it's all about interpretation, has been said already in this conference. We want the scientists to be spending their time doing what they're best at, which is making sense of the science. Now, I'll just quickly show you an example of another response there. Again, it's going to fire up on the wrong window, so let me pull that across. There is a slight glitch in my code, which is that it will fit the model perfectly and update in the background when I work on the first response. But if I look at a subsequent response, it doesn't quite update correctly. So I suspect that's down to my fault as being a poor Python programmer. But the general principles still remain the same. I select my response, I select my chosen p-value, and the tool performs that step-one analysis. It tries to work out which factors are active. And in this particular case, for my third response here, I'll just pick out the time output here. If I've chosen a p-value cutoff of 1, then it's telling me that the best first order model for my YME pseudo response involves factors A, B, D, and E, which falls foul of my rule for proceeding to step 2. It tells me that actually we picked out 4 here, so we can't go any further. So what I could do is accept that. So, well, okay, looking at these numbers, okay, that might be sensible. As a scientist, do I think, in terms of my time response, flow rate, pH, dilution gradient, do I think that these factors might influence time? Or should I be a bit stricter with what I let through that gate in terms of being declared an active factor? And rather than using a p-value cutoff of 0.1, maybe I should be a bit stricter and try a p-value cutoff of 0.05. Now, if I do that, then rather than 4 factors being deemed active, only 1 is. Only my first factor is important enough to be included in the model. So I've only got a single factor, which is factor A, flow rate. But that then allows me to go on to step 2 and look at, for example, the A squared quadratic term as well. And it's deemed that that's a better model. They're not including that quadratic term, so therefore the best overall model is inset plus factor A plus the A squared term. And again, it has fitted that. It hasn't updated in the background. If I go into the time response and click onto the ANOVA tab, we'll see that it is fitted that model too, involving the flow rate factor and its quadratic term. And we'll see that that's borderline significance. So again, the scientist is now left with one decision to focus their efforts on. Do they think it's sensible, worthwhile, valuable, useful to allow flow rate to take a non-linear form? You know, do we think that the curvature caused by the flow rate factor is worth the cost, if you like, of including that extra term in the model? And that's up to the scientists to review and determine. But what we want to do with the tool is focus their efforts on the right things. And we want to take away from them the pain of going through this process manually. So that's pretty much it. Now, what I want to do is really just summarize what I've been attempting to show today. That is the example, definitive screening designs. It's a fairly unique design structure, and therefore we can't expect the general purpose analysis methods that we use day in, day out to necessarily give us exactly what we need for them. So in this particular case, I would argue there's a benefit in setting up a one-off solution to handle this unique type of design. Another potential benefit of being able to extend Stat-Ease 360's functionality through Python is we can automate things. So if you routinely go through the same process, pulling data into Design Experts, setting up designs, whatever it may be, you can automate that using Python. If it's a very complex method, again, a bit of automation could, be extremely helpful. And if you're perhaps a statistician or a data scientist who's working with lots of experimenters, you could perhaps set up tools that encourage or force the everyday experimenters to use the most appropriate tools and analyses through your custom tools. We can do all of these things now. We couldn't before. So I really do applaud Stat-Ease for this new software package. I think it's absolutely awesome, and it really does open up a whole world of possibilities in terms of letting us do anything and everything we can imagine. And as I said before, if I can do this with a bit of Google and a bit of trial and error, anyone can. Okay, that's it. I would just like to thank my colleagues who've helped me with this talk. I'd like to thank all of our friends at Stat-Ease, especially Sherry, who invited us along today. I would also like to thank everyone who actually uses DOE. The reason I like DOE is because it's so practical. It's not statistics for the sake of statistics, it's practical problem solving. And it's only by applying DOE to more demanding and interesting things that we're forcing people like Brad Jones and Chris Nackstein to come up with things like definitive screening designs. And it's only by continually pushing the requirements at the likes of Stat-Ease that they continue to make things like Design Expert and Stat-Ease 360 better. So I think it's important we do keep pushing the boundaries and seeing what we can do. And finally, of course, I'd like to thank you all for listening. I hope it's been a useful and hopefully thought-provoking talk. As I say, I'm not trying to convince you anything about DSDs. What I want to show is how easy it is to build solutions to problems using Python in Stat-Ease 360. Thanks, Sherry. Back to you.
Thank you so much, Andrew. I learned a lot in this presentation. I'm wondering, and I realize that your goal was simply to demonstrate the seamless use of Python. In fact, you achieved that so well that that especially with that final little interface, the GUI interface, it appears that Python isn't doing anything whatsoever. It seems like SE360 is doing that work. So can you just reiterate why, in this particular case with the DSDs, Python was needed to, what function it performed that Stat-Ease 360 couldn't do?
Of course, yeah. I mean, it's kind of on this poorly handwritten slide here, I suppose. Now, all of these steps can be done manually. I imagine we could do most, if not all of these in Stat-Ease 360 if we wish to, but it will take time, it will take effort. And of course, if we're doing things manually, we're introducing a greater risk of making mistakes. So what the Python code is doing behind the scenes there, and you're absolutely right, Sherry, of course, it all happens there in the background, which is kind of what we want with the program. It just it to happen and us not have to worry about it. But what Python is doing for us in this particular example, it's creating a main effects model from our original response, and it's then using that to build a hidden YME pseudo response. So a new column of numbers based on the original set of data. It's then going through an automated model selection method using a forward selection direction with p-value cutoff according to the user's preference, 0.1, 0.05, whatever. But it's supplying those or calculating those p-values with an adjusted or corrected degrees of freedom estimate to reflect the nature of this definitive screening design. And that's something else, as I understand it, and please correct me if I'm wrong, Stat-Ease folks, that I don't think Stat-Ease 360 would automatically do. The next step that the Python code is automatically doing, it's determining whether we've got more than 3 factors or perhaps less than or equal to 3 active factors, and therefore whether we can proceed to the next round of work, which is to then calculate this y-second pseudo response, which it does again automatically in the background. And it then determines all the possible second order terms. So having worked out, for example, I think in one of the responses, it picked out factors A, B, and D as the active factors. The code will then build the list of all possible second order terms, assuming a hierarchy. So that will be the A, B, AD, and BD 2-factor interactions, the A squared, B squared, and D squared terms. So again, rather than us having to manually select and deselect terms, it does that automatically for us. And then it fits every single one of those models and every possible subset of that list of second order terms. And it does however many iterations that would be through a least squares fit. And for every single fit, it calculates an adjusted R-squared metric, and then it remembers the one that gave the best result. Finally, it then pulls that all together. It remembers all the meaningful output that's been generated along the way, and pulls it all together in the form of a combined model, which it then goes back and plugs into Stat-Ease 360.
Great. Going back to that YME response, is that the model that is just like A plus B plus C plus D, et cetera? Just the main effects? Is that the model that you're doing?
That's absolutely correct, yeah.
Yeah. Okay, so.
And then what it's doing is it's just predicting for every one of, in this case, our 13 runs, what the expected value will be from that main effects model.
Yep. Okay. Okay. Arvid asked, he says, let's see, you mentioned using designs of size 2K plus 1. I thought I heard Brad Jones mentioning the desire to add a few more runs than this for lack of fit degrees of freedom. Do you intend to do this? How many more runs? Have you guys given any thought about that?
Yeah, I mean, that's the current recommendation. When you're building your DSD, the current best practice is to include fake factors effectively. It's now, I think, pretty broadly accepted, pretty universally accepted, I should say, that the affinity screening design in its leanest form doesn't leave much room for error. So if anything goes wrong at all, the whole thing collapses. So what people are, I think, are very sensibly now proposing is that we include a few extra runs simply to give us a few more degrees of freedom, allow us to estimate a few more things potentially, and give us a bit more robustness and safety in terms of actually constructing the design. So again, I've completely dodged the question about whether we should be choosing to run a DSD, and if so, what sort of design choices we should be making when doing that. As I say, my illustration is really, once you've made your choices, how do we then analyze it as best we can? Just to add one specific point about those fake factors or those extra 4 runs. At the moment, I don't believe my tool would handle that particularly elegantly. I suspect my tool would get confused and try to include those dummy factors, and it would all come crashing down. But again, it's custom code that I've written, so I can go and fix that. And again,
Right.
that's, to me, the beauty of having the possibility of writing code to solve our own problems.
Wonderful. Okay, sorry, I am trying to get my question pane correctly open again. Let's see. When you split the Y response into 2 orthogonal pseudo responses, is this done using principal components or PLS? PLS would be helpful with overcoming the partial aliasing of DSD design, right?
Yes, and this is where I play the I'm not a statistician card, I'm afraid. I believe it's a similar principle. I think it's really trying to decompose the response into orthogonal components. So I think conceptually it's probably a similar goal, but the way we actually generate the numbers is actually probably a little bit simpler. As I say, it's just a case of fitting the main effects model to our original response, and then predicting for each run to produce the YME response, the second pseudo response. It's just the difference between the original Y value and the YME predictions. I mean, if anybody does have any questions and wants to sort of delve into more detail on this analysis method, there was a link earlier in the presentation that my colleague Paul wrote, which provides a lot more information about the DSDs and the analysis of them. Or people are very welcome to contact us either through yourselves, if that's right, Sherry, or via the contact link I've got on the slide here.
Yeah, all right, wonderful. Well, I think we've reached the end of our time for your session. Andrew, I want to thank you so much for your contributions. This was wonderful. I learned a lot, and I'm sure everybody else did too. So thank you very much.
You're very welcome. Thank you for inviting us.
Yeah.